the second type of technology I want to mention here is this nuclear norm-related technologies. So, what is nuclear norm?
I have
Yep.
one more question. So,
Yep.
so if we only consider the ranking of the approximate matrix, do you, so is NMF is still suitable for solving this kind of problem? If you only consider the ranking of the entry in the approximate matrix,
Ranking of the
Yeah, like
entry, what do you mean?
like a recommendation, we don't consider the real value. It not necessary to be negative or positive. We only consider the ranking. We only want to pick the highest one. So in this case, is NMF still a good matrix a good way to solve compared to normal matrix factorization?
Of course, there are lots of different choices, right? For example, rank SVM or whatever. But I do see a lot of works on like information retrieval recommendation. I mean, use this matrix type of technologies. I think I cannot give you a confirmative answer, but you can compare them to see whether you can get a good, I mean, which algorithm performs better. Okay. So what is nuclear norm? So one typical application of this nuclear norm type of technology is this matrix completion problem. So basically, this problem starts with an incomplete matrix M. So basically, M is this, let's say if X is the size of n by M, then M is with the same size of X, but a lot of the entries are missing. So say we only know a certain set of entry values in M, and for those known entries, their indices are stored in this set omega. And so the problem of matrix completion is to learn a complete matrix X, which can best approximate the incomplete matrix M on the known entries, while at the same time with the minimum rank. So this is a matrix completion problem. Actually, a lot of the real application problems can be casted into this framework. For example, collaborative filtering, right? You have a user item rating matrix, but you always know only a portion of them. So that's why you want to do prediction. You want to predict the rest of the missing values. And I think the reason why here we want this the rank of X to be minimal is because we want to learn X to be have a good generalizability, right? So actually minimizing this rank minimization problem is NP hard. It is intractable to solve in the practice. So one common relaxation is to, instead of minimizing the rank of X, we minimizing what we call this nuclear norm of X. Actually, here the nuclear norm of X is basically the summation over all the singular values of X. Actually, you may wonder why. I mean, what is the relationship between this problem and this problem? I referenced here from Stephen Boyd from Stanford. So I mean, which clearly stated, I mean, how this can be relaxed into this form. So okay, so here we got the nuclear norm. I mean, minimization formulation to the matrix completion problem. Actually, to solve this nuclear norm minimization problem, actually there are quite a few approaches, and I also listed here. Also, I mean, for the ones I listed here, on those websites, you can download their software to solve basically for different kinds of problem. I mean, you may choose the one that is best, I mean, fit into your problem. And I also listed the corresponding references if you want to know, not only use, but also want to know why it can solve the nuclear norm minimization problem. So that's for low rank approximation. So is there, I mean, any other question? Yeah.
Have you ever compared the non-negative metric factorization versus probabilistic metric factorization?
Actually, I want to ask your comment on what's the exact difference between NMF and the probabilistic matrix factorization.
It's lab.
Yeah, actually, In my mind,
Yeah, that's probably the question I want to ask because probably we only can sometimes for non-negative matrix factorization we do not consider the ranking.
right,
It's
right.
a ranking problem, so I just don't know based on
Right.
my experience.
Right, actually, I also have some personal experience on basically either derived an algorithm from either NMF type of framework or a probabilistic type of framework. But personally, actually, I do not clearly see the difference. Actually, you know, the benefit if you formulate the matrix factorization problem in a probabilistic framework is, you know, in matrix factorization, you always have those different kinds of regularization terms, right? If you have a lot of regularization terms, then that means you have a lot of trade-off parameters, right? So I think in probabilistic matrix factorization, you can add some like Gaussian prior on those parameters, but when you add those, then you also have, I mean, hyperparameters. Right, so that does not eliminate the free number of free parameters in the matrix factorization problem. So personally, I do not see. I mean, what is the? I think maybe probabilistic matrix factorization is more easy to extend to out-of-sample data. That might be one because they have that. Extension to out-of-sample, right? But for NMF, I think you need to play some trick to make that. That might be one benefit. Okay. Yep.
So, what is Lorentz approximation technology being applied for the binary matrices?
Binary matrices?
Yeah.
Yeah, actually there I didn't list. That's a very good point. Actually, recently there are quite a few papers on binary, NMF for binary matrices. You can constrain X, the data matrix to be a binary one and F and G to binary. And I think you may want to look into some of Professor Christine's paper. He has some paper. Also I think from Professor Ye's group, there is also a KDD paper on binary matrix. I think I can tell you offline.
Okay.
Yeah. Yeah.
So my question is that for it's the range of the elements that some of them are mostly just one issue, but some of them can be like seven sorted. So this for this kind of school metrics. So do you have a good solution for this kind of data?
I'm thinking of that's a good problem. I also observed that in some of my researches, but I think you need to do some sort of normalization before, instead of directly apply NMF. Depend on your domain knowledge, right? You don't want some elements to be tens of thousands, some elements to be less than zero. Between 0 and 1, does not make sense.
But if you normalize, so you can make all the values that's also possible.
I'm not saying that, for example, you just use some normalize them to have a unit norm or something like that. That will cause the problem you said. But apply some domain knowledge. For example, in some of my research, for example, in healthcare, right? You have a patient by feature matrix. For the features, it can be the frequency, right? It can be the frequency of specific diagnosis code over 1 year. It can also be the value of some lab test depending on your feature, right? The lab tests, they can be, for example, blood pressure and also HbA1c, all those different kinds of measures with completely different ranges, right? What we do is that we transform each lab test into a bag of diagnosis code type. Basically, we first chunk the lab test into 5 different regions. For example, if the value is below this, then it is critical low, or normal, or high, or critical high. In this sense, each lab test basically becomes split into 5 different features. Then you can still count, right? It becomes a frequency. So then this solves the basically the different scale, I mean, the problem, right? So I mean, apply some domain knowledge instead of straightforwardly normalizing. So that might be some, because I mean, I do not know your specific problem. I mean, I don't know whether, I mean, that applies to, but I think domain knowledge definitely makes sense here. Yeah.